This begins EE 569 discussion on Tuesday, September 17th, 2013.
Okay. Hello, everyone. Thank you for coming to my discussion session. My name is Hyun-Seok, and I'm one of the TAs of this class. Okay, so actually this is my first time to lead the discussion at USC as a TA, so I'm a little nervous, but I'm trying to do my best. Okay, so let's start. So this is an outline for today's discussion. So first of all, I have a couple of announcements. And after that, I briefly talk about how to write a good report. And then I'll discuss some course-related topics, especially for problem number 2 and problem number 3. And lastly, I'll introduce you to a special topic that is about how to assess the perceptual quality of an image. Okay, so here are a couple of announcements. Actually, I changed the location of my office hour from PH 330 to EB 435. And the date and the time are the same as the before. Every Thursday from 4 p.m. to 6:30. And secondly, the due date of homework number 1 is coming. So it's this Sunday, midnight. So please work hard. And as Professor Koo already mentioned, the late homework will be handed later according to the Professor Koo's instruction. So please don't ask TA about the policy for the late homework till then. And even if you cannot finish everything on time, so I suggest you submit whatever you have. It's definitely better than submitting nothing. And homework number 2 will be posted on the website this Friday. Okay, so I think most of you guys already have already started to write your report. So I briefly talk about how to write a good report. Okay, so how many pages should you write? Actually, the simple answer to these questions, it depends on your font size, the size of figure, something like that. But please remember that longer report doesn't always mean better report. The more important thing is that you need to address your in-depth discussion about your experimental result and the approach you have adopted for the problem. And secondly, you need to emphasize your idea and contribution. So that makes your report make different from others. So to this end, you can use figures and tables, examples, to strengthen your idea. So here are some important considerations in grading. So please do not copy the problem on your report again. So please do not rewrite all the sentences on your report again, so just to make your report longer. And do not copy the materials from the internet, such as Wikipedia. So if you really need to borrow some concept from the internet, please remember that you should cite all the references you used at the end of the report. And then please do not copy all of your source code. Yeah, in case you really need to write down some source code to explain your concept approach, please use pseudocode instead of full standard programming source code. So actually, it's a better way for grader to understand your idea. And then again, better result does not always mean good report, better work. So yeah, of course, better result means your algorithm is good, but you need to explain why your result came from. So you need to address your in-depth discussion about that. So better result doesn't mean you can get a free credit for the problem. Okay, so here is a sample template. So you can refer when you write your report. So for each problem, the structure is like this. So first is motivation. So in this section, you need to what the importance of this problem is. And in the second section, which is approach, you can describe the approach you used. For example, the structure of your denoising system and parameters used in non-local algorithm. So in homework number 1. And thirdly, you need to show your experimental result. So in this part, you can use figures and tables to show result. And again, you need to pick several topics about your result and discuss them in details. Okay, so now let's talk about homework-related topics. The first one is image enhancement. So in this example, actually this is not the same as your homework problem, but this is a similar problem that is about contrast enhancement. So in this example, the 4x4 grayscale image is given, as shown in this figure. And each pixel is represented with 3 bits, which means the dynamic range of intensity value is from 0 to 7. So first, we need to apply full range linear scaling to this original image. And secondly, we are asked to apply histogram equalization based on cumulative histogram method. And thirdly, we need to apply digital implementation of histogram equalization. So actually, these are 3 algorithms Professor Ko explained in the lecture for the contrast enhancement. So before moving on a specific topic, the first thing we need to do is find out the original histogram. So I think most of you already know that how to generate histogram from the given image. So basically, x-axis represents the pixel intensity value. The y-axis represents the frequencies of the intensity value. So in this example, for example, we have 4 pixels with intensity 1, 1, 2, 3, 4. So the frequency of this pixel value is 4. So in a similar way, you can generate a full histogram. So let's talk about full range linear scaling method first. So here our goal is to find out mapping function from F to G. So the transfer function, so it is called the transfer function, and the transfer function of the linear scaling method is like this. So I just copied this equation from the lecture note. So the first step is to find out 4 parameter values. So in this equation, there are 4 parameters which are fmin, fmax, gmin, and gmax. And what are the fmin and fmax? Fmin is the smallest intensity value in the original image. The fmax is the largest value in the original image. So in our example, fmin is equal to 1, and the fmax is equal to 4. Then similarly, gmin and gmax is the smallest and the largest intensity value in the contrast enhanced imaging. So because we want to fully extend the dynamic range of intensity value, so in our case, and we are using 3-bit representation for intensity value. So gmin is equal to 0 and gmax is equal to 7. And second step is to obtain transfer function. So So by applying these parameter values to this equation, we can get a transfer function. So in this example, transfer function is g is equal to 7/3 times f minus 1. Now we can do mapping. So for example, the intensity value 1 in the original image is mapped to 0 using this equation. And the intensity value 2 of the original image is mapped to 2.333. However, we cannot use the floating number for the intensity value. So here we need to do some rounding operation. So the final value is equal to 2. So in a similar way, you can calculate all the intensity value in the contrast stretched image. So this is original histogram, and this is a resulting histogram of full range linear scaling method. So as you can see, the dynamic range of the original histogram is extended a little bit. And this, from this plot, you can also observe that the dynamic range of the original image is from 1 to 4, but now we got full dynamic range from 0 to 7. Okay, so let's move on to second method, that is the histogram equalization based on cumulative histogram. So here, first step is to find out the cumulative histogram of the original image. So this is the equation. So in this equation, the denominator term is nothing but normalization factor. And basically, you can find out the CDF value of this histogram by summing to the all the frequencies from 0 to certain intensity value. For example, if we want to find out the CDF value of 3, we can sum all these frequencies together. So now we calculated all the CDF values. And then second step is to find the mapping function from F to G. So this is the formula of the transfer function of cumulative histogram method. So I just copied this formula from the lecture note. So Professor Ko already explained in the lecture how to derive this equation. So if you are not clear about this equation, you can go over the lecture note. So actually there are some mathematical expressions to derive this equation. So again, we want to fully extend the dynamic range. So G mean is equal to 0, and G max is equal to 7. So therefore, our transfer function will be like this. Here, f sub of k is the CDF function for pixel value k. So we already calculated all the CDF value in the previous slide. So we have those information here, and we have a transfer function. So now we can do mapping. So we can calculate all the mapping value from this equation. So this is the resulting histogram. So again, the dynamic range is a little extended compared to the original histogram. But actually, there is a difference compared to the histogram of the linear scaling method. Okay, so this is the third method, that is histogram equalization based on digital implementation. So sometimes this method is called bucket filling. So the preparation step for this method is to make a long 1D array like this. And next, we need to sort all the pixels according to the intensity value by ascending order. So for example, in this example, we have 4 pixels with intensity 1. So we put those 4 pixels at the beginning of the array. After that, we put 6 pixels with intensity 2 and something like that. And then here is a bucket. So what does bucket mean? Actually, bucket is nothing but the total number of the intensity values. So since we are using 3-bit representation in this example, so the dynamic range of the intensity value is from 0 to 7. So we have 8 buckets. So now we are ready for digital implementation. So the first step is to find out how many pixels go into each bucket. It's very simple. Yeah? 16 divided by 8 is 2. So 2 pixels a bucket. And then second step is to simply assign pixels in the original image, more concretely in this 1D array, to the corresponding bucket. So this is the result. Actually, this method is more intuitive way compared to the cumulative histogram method. And you will see the resulting histogram will be more desirable. So before showing the result, so here is a quick question. So there are actually, in this example, there are actually 4 pixels with the intensity value 1, 2, 3, 4. Then how do I know which to go to bucket 0 and which to go to bucket 1? There are actually more than one way to do this, but the most general way is like this. So we usually do this based on certain order, such as the scanning order. For example, from left to right, from top to bottom. So in this example, we can search the pixel with the intensity value 1 from top left corner. Okay, so for example, we can travel all the pixels from left to right on the first row. And when you reach it to the last pixel on the first row, we can go back to the first pixel in the second row, and something like that. So this is called row-wise scanning. So this is one way. Actually, there exist more fancy ways to do this, but actually, it doesn't matter. So it doesn't affect the resulting histogram that much. So yeah, this is the resulting histogram of the digital implementation method. Yeah. Actually, I prepared the extra slide for that, but I take up because I have a lot of things to do today. So let's talk about after this discussion. Yeah. Okay, so now let's compare 3 resulting histograms of 3 methods. So in this slide, this is the original histogram, the histogram of linear scaling method, cumulative histogram, and digital implementation. So what do you think? Which one is the best in terms of the contrast enhancement? Yeah, the digital implementation provides the best result. So why is it? Actually, there are 2 reasons. First of all, in this histogram, each intensity value has at least 1 frequency. So in other words, it means this histogram is using full dynamic range. So it's the one of the goals for the contrast enhancement. How about the frequency shape? So I mean, this frequency shape. Yeah, so we want to make the frequency shape as flat as much as possible, right? So in that sense, for these 2 reasons, we can say this method provides the best result. Actually, there is a difference between these 2 methods too, but I'm not going to tell about that today. So, but you need to think about that. So, the difference between these 2 methods. Okay, so now let's talk about noise remover. Okay, so in problem number 3, you are asked to eliminate this mixed noise from original image. So you need to try your best to remove the mixed noise. But we already know that there are 2 types of distortions in this image. The first one is the uniform noise. And in our problem, it's a Gaussian noise. And second type of noise is impulse noise. And in this problem, it's salt and pepper noise. So to remove the mixed noise, we need to do some kind of filtering process. What are the important factors to efficiently eliminate the noise? So the first factor is the filter type. Actually, you can use either linear filtering or nonlinear filtering. And sometimes you also need to adjust the size of the filter. And secondly, you also need to, filter order might be important. It depends, but filter order might be important. So for example, suppose that we are using two filters, filter A and filter B. And one scenario is that using filter A first and followed by filter B. And second scenario is just to swap the order. Then does it affect the final result? It depends on the situation. And of course, the total number of filters are important. So you can use 2 filters, 3 filters, and so on. So I suggest you try many combinations of filters by changing filter type and the filter size, the filter order, and number of filters. And you need to find out optimum strategy. But more importantly, you need to explain why you choose such a scheme as the optimal solution. Okay. So here is my hint for this problem. So I suggest you observe the histogram of each channel. Then based on that observation, you can decide which filter should be applied to each channel or each distortion type. So for your understanding, I prepared one example. So this is the original image, and this is a histogram of the original image. And I applied 2 different types of noises. The first one is Gaussian noise and salt and pepper noise. And these are 2 histograms of these 2 images. And clearly you can see there is some characteristic in this histogram and in this histogram compared to the original histogram. So for example, if we see the histogram of the salt and pepper noise image, you can see 2 peaks at these 2 extreme points, pixel intensity 0 and pixel intensity 255. So do you know why there are 2 peaks at these 2 extremes? It's very simple. Yeah, salt usually have the pixel intensity 255, and the pepper is usually 0. So simply by observing these 2 noise the image, simply observing the histogram of the noise the image, you can decide which distortion is applied to the original image. So by the observation, based on those observations, you can choose your filter type, linear filter or non-linear filter. So this is one hint to solve this problem. Okay, so now I introduce a special topic that is about how to assess the perceptual quality of an image. So actually this field is called either perceptual quality assessment or objective quality assessment. So the most commonly used image quality metric is PSNR. So have you ever heard about PSNR? Yeah. PSNR is calculated by this equation, so 10 log 10 max square divided by MSE. So here MSE means mean squared error between 2 images. So if you see this equation, MSE is nothing but pixel-wise difference between 2 images. So in this equation, X represents the original image and Y represents the filtered image or distorted image. And max is nothing but constant, maximum pixel intensity. And in image processing, we usually use the 8-bit pixel representation. So the max will be 255. So the motivation of this field came from the fact that PSNR is not good enough to represent the perceptual quality. So this is the example. So in this slide, this left figure is the original image. So there is no error in this image. But if you see those 4 different images, you can clearly see the difference in quality. So the qualities of these 2 images is much better than the quality of these 2 images. Do you agree? Yeah, but if you calculate the PSNR value, all those 4 images have the same PSNR value, 225. So it means that PSNR is not good enough to represent the perceptual quality. So we need better metrics for that reason. So when it comes to, say, quality score, there are actually 2 types of quality. The first one is the subjective quality score, and second one is objective quality score. Actually, subjective quality score is nothing but human score. So human rate the image. So it's kind of ground truth score, basic score, or reference score. So mean opinion score is sometimes called mean opinion score, MOS. And this is the most trustworthy score. But the problem is that it's really time-consuming and expensive way, because we need to ask people to rate quality of the image. So we need a more effective way to rate the quality of the image. So that's the reason why we need the objective quality metric. And PSNR has been used for a long time, about 20 years, because it's very easy to compute and very easy to be implemented onto the automatic system. But as you see in previous slide, it is not that consistent with the human score. So in this field, our goal is to find another objective metric that has a high correlation with the human score. So actually, yeah, to develop more better score, actually we need to investigate the human visual system. Actually, human visual system extract structural information when people see the scene or object. And some distortion type does not change the structural information. So we look at this example. So this is the original image, and this is contrast stretched image. But in this case, there is no loss of the structural distortion. So all the structural informations are preserved. But some distortion results in loss of structural information. So for example, this is the JPEG compressed image and blurred image. So you can see, if you see the object boundary and edge, the edges are deteriorated by the bracking artifact in this case, and there is a lot of blurring. So there is a structural loss in these 2 images. So based on these observations, the structural similarity index, so-called SSIM, SIM index, was introduced about 10 years ago. And the idea is that structural information is dependent of the luminance component and contrast component. And justification came from the study of human visual system. And actually, human visual system is based on 3 independent components: the luminant component, contrast component, and structural component. And these are the mathematical expressions. So for example, given original image X and distorted image Y, you can compute the similarity between each component, each three of each component, each of 3 components. So this is the luminance similarity, and contrast similarity, and structural similarity. So finally, we can combine these 3 components together to get a single SIM index of the whole image. So actually, there are some mathematical procedure in between, so I just put the final result here. So this is the SIM index. Okay. Yeah, I presented so fast. Actually, yeah, this is the last slide of this discussion. I failed to time management today, so please understand. This is my first time. So yeah, I do better next time. Actually, yeah, but
The
maybe
time is
you
12
might
o'clock.
use the SIM index in the homework number 2, homework number 3. So today I just introduce the very brief information about SIM index. But maybe next lecture and next discussion, I'll give you more detail about SIM index. And this slide verifies why SIM index is better than PSNR. So again, so this is the original image, and contrast stretched image, mean shift image, and compressed image, blurring image, and salt and pepper noise image. So if we calculate PSNR value, actually all these 5 images has very similar PSNR value one another to 25 something. But in case if we calculate the SIM index of each image, it's different. For example, this image has a SIM index 94 and 98 and 67 and 68, 72. It means, according to the SIM index, this image has the highest quality, and this image has the lowest quality. So it makes sense. So yeah, but still it depends on the situation. There is a reason why people are still using PSNR for 20 years. The SIM index is more close to human visual system. So when it comes to say perceptual coding, perceptual quality, SIM index is a definitely better way than PSNR metric. Okay, so that's all for today. And, yeah, because we still have a time. If you have questions about homework, please come to me. We can discuss together. Okay, thank you for coming.
I'm just confused. Like, let's say I have, like after I divide up into 256 bins, I have like 100 left. This has been E569 discussion on Tuesday, September 17th, 2013.